Now, more difficult examples will contain a log expression that is not to the base e, and in order to do that we'll have to use the change of base rule. I think I touched on this earlier in a video and said that it would be one of the more difficult rated questions. So what are we going to do with this example 1 where it says find d dx of log of x to base 10? Well, first we must recognise that it is to a base other than e. So we would start off with this is exactly the same as d dx of the log to base e of x over the log to base e of the number 10. Now, it's important to realise that log to base 10 of e is just a number. It doesn't involve any x. It's a constant. So we'd have to think about how you differentiate with a constant. And so we want, I might actually just write it like this, just to, you don't have to, but just to make the point that it is like a coefficient sitting there. So to differentiate that, I would keep my coefficient and I would differentiate this, which is 1 on x. Nothing difficult about that, and I don't do anything with that, it's just the coefficient, so it sits there. And that example is quite different because often when we differentiate a log, we see nothing in the result that resembles the word log, but in this one, that's not the case. We are actually seeing log. It's certainly not log of to base e of x, but it does still have the word log in it. Now, hopefully when you look at this example, there's a lot you noticing is going to be a problem. So we have a power of x, and we certainly haven't learned how to differentiate a function when x is the actual power. And in fact, we don't. We have to make a connection to the fact that x is in that position and rewrite it in a format such that we can differentiate. So that's exactly what we do. We've got here y is equal to 2 to the x. By the definition of a log of a number to a given base is the power to which the base is raised. So I could say that very statement is exactly the same as log of y to base 2 is actually equal to x. So the log of any number to a given base, and the base I'm choosing is 2, would be x. Now, you might think that's not very helpful, but what we could do is differentiate x with respect to y. So that's what we're going to do. We're going to now differentiate x with respect to y. But beforehand, we will need to write x as change of base rule, which is 1 over log to base, and I'm going to introduce my base e, of 2, which is a constant, times, and we would have on the top log of y. So it would be log of y over log of 2, change of base. So we can differentiate x with respect to y, and this is, like I said, just a coefficient or a constant, and the derivative of log of y, because it's now to the base e, we can differentiate that, and we would call it 1 on y. You may be wondering what that has to do with y dash. If I turn this now upside down y dx, and I turn this side upside down, I've got log 2 times y, or log 2 times, what's my expression for y? Y is 2 to the x. So to y dx, or y dash, is equal to 2 to the x times log of 2. Now that one is very, I don't know that it's very difficult. It has connections to concepts that are not obvious, and maybe that makes it difficult. Most students learn this one. They would put it in their summary. They know it's of the more difficult type, and it has that complication of needing to make a connection to something that's not so obvious, and do the little technique of finding dx to y, not to y dx, and then turning it upside down. It's a great example to look at because the features that are required to get through the solution are not very common features. However, they're good to observe and certainly be aware of. Now, just as you saw that we had to introduce the definition of a log in this statement here for us to be able to get working, so we took the expression as it was given, used the definition of, if you take the log of a number to a given base, then you've got it equal to the power. Now, just like you saw that concept there, you will now and could need to use your log rules with a question or in a particular situation. Now, not that it's necessary, and I would just stick to this. These are some interesting approaches. If you had to find the derivative of log of 7x, for some reason, I guess you could say, well, the log of 7x is actually, by definition, the log of 7 plus the log of x. So the d dx of log 7x, the derivative of this, the log of a constant, well, the derivative of a constant is 0, is nothing, and the derivative of x is 1 on x. Now, that seems like we've lost some valuable information, but in fact that is the correct answer, and the answer we would get if we hadn't chosen to complicate it with this, if we'd just gone straight to d dx of a log is d dx is equal to 1 over the 7x and multiply by the derivative of 7x, which is 7. The 7's cancel out, and you get the derivative is 1 on x, which is what we got there. So this might seem like a long way around doing it, but there might be some cases where you'll choose to do it that way. I don't think there's anything unusual in what's going on here. We could look at the derivative of the log of x on 7 and realise that that is a fraction and think of it as two separate logs. And so you would have that d dx of x on 7 could be separated into, so this is just using the log rule, separate it and put a subtraction. Now to differentiate, I would differentiate log x, and log of x gives me 1 on x, but log of 7 is a constant. It's a number, it doesn't have any x term in it, and differentiating constant you get 0. So we're finished. Or I could use my previous rule for derivative, and that is the derivative y dx or d dx would be 1 over, here's my 1 on function x, so I want 1 over x on 7, and I'm going to multiply by the derivative of x on 7. The derivative of x on 7 is 1/7. What does that look like? It's 1/7 times 1 divided by x on 7 is the same as 1 times 7 on x. And you see the 7's cancel out and you get 1 on x, same answer. Like I said back here, it was just interesting approaches. So you can use your log rules and you'll end up with the same result as differentiating, leaving it intact as a function.